It's just past 3 o'clock. Welcome, everybody. Hello, everybody. Good afternoon. Good morning, wherever you are. Welcome to this webinar on the industrialization of friction stir welding. We have over 600 people registered today, so it's very busy. We're very pleased. Just before I start a little bit more, I will let you know there will be a repeat of this webinar on November 19th at 7 a.m. GMT to allow those of you who are staying up very late or have got up very early to attend on a more Asia-friendly time, if that helps anybody. It is on our website if you look, or we can send you a link. Next slide, please, Jonathan. So today we are going to be talking about the industrialization of friction stir welding for steel. You'll hear from 4 different experts. Dr. Mike Russell from TWI, who's the operations director and was front and center in the development of friction stir welding of aluminium back in the early days when it was invented by TWI. Abhishek Tanwar, who's been directing things for Element 6 and the development of the tools, and one of the partners that we are working with. Jonathan Martin, who is the section manager and expert in friction stir welding of steel, will deliver the results of the work that we've done over the last few months and where we've got to so far with friction stir welding of steel. And Dr. Santonu Ghosh, who will give you an update on the tool life and the toolware that has been developed for this process. Next slide, please. Jonathan, next slide, please.
Yeah, I'm sorry.
I urge you all to relax, take a seat, get a cup of tea like I have, and listen to the experts. We will take questions in the Q&A box at the bottom. I will endeavour to ask as many of the questions that's come through, but with well, we've got over 300 people on so far and 600 registrants. There will be a lot of questions, and I'm sure we won't be able to answer them all. However, we will endeavour to come back to you in the next 48 hours as much as we can to all of those questions if we can't answer them over the time now. There is a dedicated email address, fswsteel@twi.co.uk, which will go to a number of the speakers today and is the best way to get in contact with us at the end. So without further ado, I hand over to Dr. Mike Russell.
Okay, thanks, Nick. Hello, everyone. Good afternoon, or indeed good morning or good evening, depending on where you are in the world and joining us today. It's great to see so many people joining in on the call and the great interest in this remarkable technology. And we have a good story for you ahead today, which I think you'll be very interested in. So some of you will, of course, be familiar with TWI and with friction stir welding. But by way of introduction, there are some people joining us today who are new to this area and new perhaps to our work. So just a couple of slides to outline TWI as a business. We are a world center of materials joining technology. We were founded in 1940s in the Cambridge area in the UK, and we've now grown to over 600 staff and revenues of 70 million, as you can see on that slide. Next slide, please, Jonathan. Thank you. So this slide summarizes our technical expertise across TWI. In the interests of time, I'm not going to read through all of these individual areas, but you will all receive a copy of this presentation. So feel free to have a look at this. And if you are interested in any of these areas as well, then please get in touch. So that's what we do. And next slide, please. That shows you who we do that for. So we are active across a wide range of industry sectors. And as you can appreciate from those images, lots of different engineering materials, different thicknesses, different scales of operation, different nations, territories, and companies. It's a very broad-based business. Next slide, please. So friction stir welding will be, of course, familiar to many of you. I'm not going to talk through the process itself here today. If you would like some more information about the base process, feel free to reach out to us or indeed look at our website. The key point here to pull out is this technology was invented by TWI in 1991 and was actually in production use in industry within 5 years after invention. And that's quite a remarkable turnaround and implementation period for a brand new process. Next slide, please. So one of the reasons for that really rapid uptake, and here we're talking predominantly about the aluminium market, was the combination of lower costs, higher quality, and improved speeds. So friction stir welding as a technology is better and cheaper and faster than the incumbent technology in that area at that time. Now, you may well say, of course, I would say that. I work for TWI, we invented the technology. But what you see here on this slide are some public domain quotes from companies who've used this technology in production. And as you can see, they are reporting cost savings, they're reporting time savings, they're reporting quality benefits. So next slide, please, Jonathan. In terms of the friction stir welding market, this is an analysis that we undertook a few years ago now at the end of the friction stir welding license. So friction stir welding was a licensed process. The core technology is now free from patent, so free for anyone to use. But at the time that that happened, we looked at the scale of the market overall, and we collected and calculated the value of that market and a number of the key performance indicators, as you can see there. So at the time, we estimated that we had probably welded halfway around the world with friction stir welding, which is not bad going in 20 years since invention. We had saved enough energy to make 200 million cups of tea. So a peculiarly English thing to refer energy savings to cups of tea. And we had saved ourselves about 2,400 tons of CO2. Now, you can probably add about 20% to those numbers to bring us up to date today. Next slide, please, Jonathan. That gives us an estimate of the market as it is today of about 50 million. And of course, that is aluminium dominated as we sit here today. So the exciting potential for friction stir welding of steel is that the steel market is itself 30 times larger than that of the aluminium market. If you look at material production each year in the world. Now, we don't expect friction stir welding to be used for all welding of all steel. You know, there are lots of good processes for welding steels, but the market is sufficiently large and the applications and benefits sufficient that there's potential to at least double, if not more, the friction stir welding market as it is today by moving into steel. So next slide, please. The question, of course, that then comes is, well, why hasn't this happened yet? Why hasn't this market realized its potential? And a key factor here, and indeed the key enabler, is the friction stir welding tool. And you're going to hear quite a lot about that today. The tool used for friction stir welding of steel obviously experiences a highly demanding environment, and that really requires a leading edge materials expertise and understanding to be successful. Friction stir welding of steel in the past has suffered from inconsistent tool performance and repeatability, variability issues. And what we're announcing today really is a step change in that position, with element 6 now moving into this area and providing a new and effective solution for this challenge. So we'll show you that in this talk, and I think you'll be excited by what you see. So that's everything from me to start with. Thanks again, everyone, for being here and for your interest in this area. We look forward to talking to you and working with you in the future. And I will hand over now to Abhishek from Element 6. Thanks.
Thanks, Mike, and a warm welcome to you all. I want to touch upon two things. One, to introduce Element 6, and then two, to talk about some of our unique strengths that make Element 6 an ideal partner to develop friction stir welding in steel applications. So we are a subsidiary of De Beers, which is a part of Anglo American. So we are proud to be a part of a large organization. And we've been providing synthetic diamond solutions to our customers for over 60 years. And our products find a wide variety of applications and end markets, oil and gas, aerospace, automotive, semiconductor, etc. We serve over 5,000 customers globally with a manufacturing footprint in 6 countries, and we are supported by a team of scientists at our Global Innovation Center near Oxford. Next slide, please. So the graph on busy graph on the left, but the one in amber is gives you a sense of our product range, and they cover a wide variety of diamond materials. We have been making PCBN, which is short for polycrystalline cubic boron nitride, for ferrous applications such as steel for 40 of the past 60 years of our existence. And they are in use in many end markets and applications such as automotive, aerospace, and others. So we make large discs, or I should say the largest discs. And why is that important? Because as we think about new applications needing maybe a deeper weld, for example, we feel we can supply that. And then we continue to invest in technology, in new product grades for unique applications. So we feel comfortable that we can create new types of PCBN to suit new applications. And I think another point to highlight is we already make PCBN in large volumes. So scaling up to manufacture for us is not an issue. Next slide, please. So one of the key questions is, how are we able to make these tools reliable and provide a consistent result? So what's so special? What's the secret sauce? And I'd say our knowledge of PCBN and working in close collaboration with TWI has been the two critical factors here. And that has been ably supported by the focus of our colleagues in our innovation center. And what we've done is we've looked at every aspect of PCBN production. So from product design to raw material, to how we make it, to how we process it. And then we test. And then we take feedback, we get feedback, and then we make changes. And this has been going on for a period of time. So we've been on a collaborative journey with TWI. We feel good about the results that I think Jonathan is going to talk about. That's all for me.
Okay, so greetings from me. I'm Jonathan Martin. I'm the Friction Stir Welding Technology Manager at TWI. So thanks for joining our webinar. Friction Stir Welding of Steel is not new. You know, we have been doing this for many years. I can remember when I joined TWI some 15 years ago, working with Wayne Thomas, the inventor of friction stir welding, joining some 12% chrome steel. And I think this picture on the screen here quite clearly sort of shows one of the major benefits of friction stir welding. This is a 6 meter long steel panel that has been friction stir welding. So friction stir welding is a low distortion joining technique. Since that time, TWI, along with other practitioners of friction stir welding, research organizations have been looking at joining steel. I don't think we've come across a steel that we can't join, ranging from carbon steels, from construction steels, pipeline steels, steels used in shipbuilding, etc., along to the high carbon D2 content steels. A range of stainless steels, the austenitic 304, 316, through to the martensitic and duplex. And also we've welded some of the very difficult to weld steels, such as the precipitation hardened steels and the ODS, which are impossible to fusion weld. And I think also with friction stir welding, it is possible to do some dissimilar joining. So this is an example of joining a carbon steel to a duplex steel. And I think universally throughout all this work and through papers that have been published, you know, the properties of these welds are I think, universally accepted as very, very good. This is due to the wrought microstructure of the nugget itself. So, you know, reported increases in strength, fatigue properties, in toughness, etc. So I think this is sort of universally known. But also, I think universally known is the issues of tool materials in terms of tool wear and consistency. And therefore, this is part of what we are looking at now in terms of trying to develop a tool that overcomes some of these problems in terms of providing a tool that is reliable and consistent. So we have been working with E6 bringing together its expertise in PCBN, materials processing, and TWI bringing its knowledge on friction stir welding. So over this 2 years, we've looked at different tool designs, looked at tool holders, plunge cycles, pilot holes, tool wear assessments, and we've come to the position really where we feel that we can share these results with you and allow us to say that we believe we have found a tool material, you know, which is robust and consistent. So we set about doing a sort of testing regime on these tools. So in order to develop the testing regime, we need to then decide, okay, what sort of applications are these tools going to be used for? So as Mike was saying, it's a very harsh environment for these tools. You know, they're sitting at elevated temperatures for many minutes, and depending on the application. So if you're looking at pipeline welding, where you would have multiple plungers and short duration welds, through to perhaps more the applications in the construction industry, where the welds will be slightly longer and therefore the plunge cycles will be less, leading through to really long welds used perhaps for panel building, for ships, etc. And these welds may be 20 meters long, and therefore the tool in these cases will need to sit at these elevated temperatures for over an hour. So in the test that I'm going to show you now, we looked at assessing the regime 2. So this is making 5 meter multiple 5 meter long welds. So to do this, we selected 6 tools. These tools had a penetration of 6 millimeters. So these were 6 tools, but there were 2 tools taken from 3 different production batches. So these aren't from one batch. These batches were made over a period of time, but they were all subject to this very close, rigorous assessment. The plate material that we welded was an 8mm S355 steel, low carbon steel, and we just took the mil scale off the top of these plates in order to reduce the number of variables, really, because we wanted to assess the tool material performance. All the welds were made in position control. So these were multiple 5 meter long bead on plate welds, and the target was to do 8. So accumulating about 40 meters of weld on each tool. And then the assessment was looking at the weld parameters, looking at the weld data logs, measuring the tool after each weld, taking a picture of the tool and assessing it for any potential damage. We then took a weld macro every weld, and then after 20 meters of weld, we then took a more detailed scan of the tool. This was done by E6, and Santonu in his presentation after mine will show you some of that work. So this is a video of one of these welds. So this is one 5 meter long weld. So I'll start this now. So as you can see here, this is the material that we are welding. There are 3 welds. So on this video, we're making the 3rd weld, and this is the tool here. So this shows the tool being rotated and being plunged into the material, heating the material up, getting it soft. The tool then transitions up the ramp phase, getting to full speed, to welding speed. So we're welding here at 300 millimeters a minute. So we're using an argon gas shield to protect the tool, protect it from oxidation. So you can see here the weld is now complete after 5 meters. We also measured the width of the weld cap to ensure that we're getting full consolidation of the weld itself. So as you can see here, these are all the plates that we welded. So each one of these plates contained 30 meters of weld. So we welded and welded. I think Chris, so our operator Chris, I think he was just fed up with the size of these plates after a bit. So this is the tool after 40 meters of welding, and this is a new tool. So it was pretty, it was done under great scrutiny, but it was pretty boring, which was good really, because nothing happened, nothing exciting happened. The tools perform extremely well. So I did mention that every weld, we took the tool, we took a picture of it. So this next slide is really showing that progression as the tool built up meters and meters of weld on itself. So this is a picture of a new tool, and these are sequential photographs of the same tool going through after each 5 meter long weld. So you can see here that the tools, in essence, there is a slight bit of wear, perhaps slightly on some of the crisper edges, just slightly rounded, but in essence, the form, the mixing capability of those tools remained. We also took a macro from every 5 meters. This is just showing every 10 meters, so you can actually see in detail, a little more detail, what the macro, what the weld nugget looks like. So very typical of a friction stir weld. You can see the raw material of the plate around the nugget and the TMAZ. So in order to sort of try and quantify, are the tools mixing the material similarly, we just overlaid on this first one after 10 meters a shape to say, okay, this covered really the nugget and the TMAZ. And then if you translate that and overlay that on all the other welds, you can see how consistent the shape of that weld was, which leaves us to believe, the consistency of mixing of these tools was very, very good. So we did take some of these tools a little further. So this was really just looking at, can these tools do 40 meters? We have taken some of these tools and welded further with these tools, looking at force control, etc. But what we wanted to prove really within this work was, are these tools consistent? If you get consistent tools, you can then say, okay, these tools can be adopted by industry, and then you can work out commercially whether it is viable to apply these to your particular application. So all these 6 tools accumulated the 40 meters without failure. The welds were consistent. We didn't see any flaws or defects in the weld that caused us any concern. The tool wear was consistent, and none of these tools failed during this testing regime. So I'd like to hand over to Santonu now to show you some of the results in terms of the scanning. And so Santonu, I'll hand it over to you.
Thanks, Jonathan. I'm Santonu Ghosh. I work for Element 6 at the Innovation Center based in Harwell, Oxford. I develop new product and technology and have been doing it for some years. I'm pretty excited to talk about the work which we are currently doing. So Jonathan has already mentioned that we have been working on this development for some times now. And the extensive trials, it's not only about the long welding trials what you have seen. We have carefully and painstakingly had taken time to develop the material as well. Why that's important, the main challenges, as you have heard already articulated by Mike and Jonathan, that the consistency of the tools are very important in application, and also the performance. So we produced tools over more than 5 batches of tools, but not only during a small period of time. We spread it over the year. So we produced batches of the tools at different intervals and different time of the year. At Element 6, we do mass production of PCBN products, and the variations we expect to see over a period rather than just synthesizing and preparing the tool in a week's time. So the tool results, what you have seen now, which were those 3 batches were selected at different time period of the year. Till now, we have tested this, taken this tool to maximum of 63 meters. That we stopped there. There are primary couple of reasons. One is, of course, some of the applications which Jonathan mentioned require certain length of the tool to be tested to. And we believe that if we go around 60 meters, we cover most of it. Whether we can take it further, yes, of course. Again, that's something that the development side we will be looking at. And the second one is, of course, it takes quite a long time to trial this tool. The why that's important is the life. So steel is a very difficult material to weld, and there are other materials which possibly could do steel welding. However, they wear very fast. That results in defects in the weld, and also the performances of all of them are not so consistent. So that's why we wanted to trial these tools to certain long distances and then measure the weld properties and as well as the other wear on the tool. So we have taken multiple tools to 60 meters. We have seen 6 tools we have tested as a part of this consistency trial to 40 meters. However, we have taken roughly around 10 tools to 40 meters and then studied the weld properties. Whoever is familiar with steel welding and also the material size of the brittle material, especially the plunging stage is the harshest one, where the tool comes in contact with hard cold metal, and the mechanical properties doesn't allow the material to survive those conditions. So for us, it was important to expose them to the harsh atmosphere of plunging. We did these plunging trials at different lengths. So it's not that we took a new tool and plunged these tools. So for example, I'm showing here that one tool which we have done 21 plunges and we stopped after that. Out of this 21 plunges, we did 10 after the tool has done 60 meters, just to test it to a more harsher situation. So in gist, we have developed and we felt we have reached a stage of development where we should share these results, because we have fairly confident that these tools will do good in various different applications. And we could extract more out of it based on the application you have in mind. And would definitely like to hear more about what kind of applications you have in mind and have further discussions. Next slide, please, Jonathan. Yeah. So Jonathan has shown the results he shared about the welding and how the macros, etc., look like. So one of the slides you might have noticed, it was difficult to pick up the wear even after 40 meters. So we wanted to scrutinize the tool more than the optical images what we had. So we used a 3D microscope, Alicona 3D imaging microscope, where we take 3D images after each 20-meter interval, overlap the images to find out the wear. And on the left side image, what you see is a differential image after a tool has worn. The pink areas are the where we have seen the wear happening more, which is understandably because of experiencing higher surface speeds. We also took the cross section to look at the profiles. So the right side, what you are seeing is the profiles from all the 6 tools which Jonathan mentioned, and again, it overlapped very well, demonstrating that the tool wear has been very steady, and we didn't see much variation among the tools. So it's not only we have seen the welds have been good and very similar, we also have seen the tools behave very similarly as well. Next slide, please, Jonathan. So we have tested these tools beyond this consistency trial. We have tested these tools at different traverse speed. So so 0.1 to 0.3 meters per minute. We have tested them under different conditions. So whether it's a position control or whether it's a force control, we have already mentioned about the plunging trials. So we have done it in different areas, different regimes. We have done it, suppose, for a 20 meter at a stretch where the tool spends an hour at temperatures above 1,000 degrees. And that actually helps us give, in saying this, that these tools are ready for where it could be applied. So if you have application in mind, we would like to work in collaboration to develop this for your application, because there are a lot of levers we have, and we feel more confident that this could be done. Over to you, Nick.
That's great. Thank you, Santonu. Thank you very much, Jonathan, and everybody else. So just to summarize where we've got to so far, I think we've demonstrated the friction stir welding of steel is now possible in a consistent and hopefully commercial way. It will give you the benefits of less distortion, a superior weld, and no consumables. TWI and E6 have demonstrated those reliable tools so far. Now there's quite a lot more work to do, and judging by the questions, I hope all the panelists are not going home tonight. We've had a lot of questions. What I'll do is I'll pick out as many of the questions as we can, and ask you as the panelists to answer them one by one. I think it was a really, really great presentation. Thank you very much, and I think it really shows that the big investment made by both companies and the really good quality welds that we're now getting. I have a whole sheet here, so I'll start with one for you, Jonathan. Santonu mentioned 60 meters. We mentioned TWI mentioned 40 meters. Is there a reason for that? And have we tested the tools to be on 40 meters?
You're on mute, Jonathan.
Don't do it, Jonathan.
Okay, I'm here. I'm back in the room. Yes, I think the work that I was describing, was this consistency testing. So yes, we have tested these tools under lots of different regimes, from multiple plungers to 20-meter lengths. But these have been sort of individual tools, if you know what I mean. It wasn't a systematic where we're looking at taking so many tools from so many different batches. Do you know what I mean? So yep, Santonu is right that we did test a lot of tools that I didn't report on, but what I was looking at and what I wanted to report was really that of the consistency. This is where I feel that it's very important, in terms of getting this technology adopted by industry. People have to be confident that if they receive a tool, that it will last. Tool breakages, tool wear, etc. A lot of these components that are manufactured are high value, and therefore it's more important that we can, in the testing that we did, was just to demonstrate that there is a tool that can stand up to this, and we chose 40 meters as the cutoff. There was a lot of welding getting to that 40 meters, as you can imagine, and I would have loved to go on to 60 meters, 80, 100 meters, but this was just not possible in terms of the resources, etc. So we reached a point in time where we could quite clearly show the systematic testing of these tools to 40 meters, but we hadn't got this systematic approach for tools above 40 meters, but we have tested tools, as Santonu said, up to 63 meters. We took the 40 meter tools and operated them in force control to further develop the process. So this is an ongoing thing. This is an ongoing development, and that's perhaps why there was a little bit of confusion between what I was saying in terms of this 40 meters and Santonu 60 meters or 63 meters.
Okay, thank you. Thanks, Jonathan. Mike, you mentioned friction stir welding patented. Is this process for steel patented?
Yeah, so the basic technology of friction stir welding is now out of patent and free for everyone to use.
Okay, so you just need the best tools. That's all. How thick can we weld? What have we gone up to? I've actually been specifically asked as well. Can we do from 1 to 5 millimeters thick in stainless steel? Jonathan or Santonu?
The tools that we have been testing here are 6 millimeter. I think the second generation of tools that we are working on now, perhaps Santonu, you could comment on this, but are looking up to 12 millimeters. So in terms of going smaller, we don't see this as an issue. You know, it is more in terms of depth, in terms of the puts the stress and the strain and the on the tool. So sort of tools less than 6 millimeters, obviously they need to be designed and manufactured, but that shouldn't hold too much fear. It's really now taking it on from the 6 millimeter up to 12 millimeter, and I know some applications, particularly in pipelines, you know, are looking at 3/4 inch 19 mil. Do you know what I mean? So I think that's a good target to go up to. So the work that we have seen here is for 6 mil.
Yeah, if I may add, Nick, on that point. So absolutely, we can go to a lower pin length. We are looking at different sizes in the development. And as Abhishek mentioned before, is that we have capability of producing larger PCB and parts and here for tools. We could in future potentially explore that options as well. What are the larger thicknesses we could go? Definitely our approach is to go step by step and make sure that we don't compromise any of the tool qualities and tool performances that we are talking about. So yeah, that's in pipeline.
Thanks. You mentioned pipeline, and Jonathan mentioned pipeline. A couple of questions about the geometry. So what geometries can be welded, and specifically pipeline has actually been asked about by a number of people.
Well, typically friction stir welding of steel, you know, is at the moment, I would say mainly butt and lap welding. So fillet corner welding has not really been developed. This is being now looked at perhaps for aluminium, and as the tool material matures, etc., for steel, this is an option then to transfer some of that technology or some of these techniques into steel. With regard to pipeline, you know, this should not be an issue. It's typically a circumferential weld, so this is a butt weld. Yep, pipe welding is not so much of a problem at all. Obviously, with pipe welding, it's really that is the support of the weld. So friction stir welding is a solid state, high force process, and in order to get a full penetration weld in a pipe, you have to then support the weld, which normally relies on an internal mandrel. But yeah, this should not be a problem.
Okay, and do we see any near-term applications that we can talk about at the moment? Anything that people, I mean, I guess pipe is one of them, but we are being asked a lot about, that we can mention? Who was asked?
I think
we have to be careful, confidential.
Yeah, I think there are lots of interest. Obviously, you know, the picture I showed early on of that long weld. So distortion is certainly one of the benefits of low distortion. So shipbuilding. You know, there's been interesting for for applying this to ships. So this is where we're looking at perhaps very long welds, so these 20-meter welds. But yeah, there are lots of different applications for this type of technology, and as Mike said, it's not going to solve all the problems. It can't be applied to everything. It's a bit like friction stir welding of aluminium. You know, there is a niche for friction stir welding. You know what I mean? Within aluminium, it's not good at everything, but if you can find what it is good at, it is very good at it. So it is a subsection really of steel welding where this technology will be applied.
Okay. A lot of questions about temperature. So the temperature. Do we cool the tool? What temperature is the weld at? How is it compared to other processes during the actual welding?
with this tool, we use a water-cooled holder, so we're not directly cooling the tool itself. It's in indirect. So within the tool holder there that the tool is held, there's a water-cooled jacket. So we are extracting heat from that tool. The temperature, we haven't done any temperature measurements on this type of while we've been doing these welds. We've been monitoring the temperature of the weld as it comes out from the back of the tool, but this is more a consistency thing, just to ensure, as part of all the data that we're collecting, that the temperature of the weld remain the same throughout these trials. So the temperature, I would envisage it's 900 to 1,000 degrees, but it's very difficult to actually measure the temperature. Do you know what I mean? Because it's where do you actually put the thermocouple? If you put it in the middle, obviously it gets destroyed. But it'll be around that area, 900 to 1,000.
A couple of questions on the tools, Santonu and Abhishek. What is the price of the tools, and are they going to be commercially available and rolled out to the market on a high volume basis?
Are they going to be commercially available and rolled out on a high volume basis? Absolutely, yes. I mean, that is the whole aspiration for us. Are they available at the moment? I think there is still work to be done. I'm not sure, Nick, if there was a question on price point. Sorry.
Yes, there was. Yes.
I think it's as you can all appreciate, I think it's early in the stage at the moment for us to get definitive around it. I think if just to kind of focus our mind, order of magnitude, I'd say if you're aware of what some of the previous cost points you've come across, I think I'd say order of magnitude if you keep that in mind. But the level of variation that we can get to at this early stage, I think that could be high as well. So order of magnitude, think about what you've seen before, but there's still a lot of work to be done.
Okay, thanks. Jonathan, quite a lot of questions around the parameters. So could you share what you can about the parameters? I think you mentioned the speed of the weld, just how what sort of forces, etc., we're seeing on these particular welds.
Well, these welds, as I said, were made at 300 millimeters a minute. The rotation speed was 350 RPM. So it is a relatively low spindle speed. The forces, perhaps for the eagle-eyed of you, saw one of the data plots there, was around 40 kilonewtons, 43 kilonewton in terms of downforce. So it is slightly higher, I would say, than aluminium, but perhaps not too dissimilar for welding, the very high strength 7,000 aluminium, just slightly higher. So, these tools potentially can be used on existing friction stir welding machines. This is, it's not like a magnitude different. I think applying these to milling machines, I think it would also be possible, but obviously I think the depth of the weld, or the depth of welding that you can use these tools on, perhaps will be limited, in to perhaps 2 or 3 millimeters. So the welding parameters are not vastly different, really, to aluminium, slightly higher.
And were they all done at the same speed, all the tests that was asked?
Yes, yeah. I mean, this was a consistency. This is the whole purpose of these tests. Was so we went through the development process of looking at welding, the weld parameters, which we haven't fully explored. So we chose a welding set. So this was 300 millimeters a minute, 350 revs, and all those welds that we made were run exactly the same, because it was really to test the tool material. So we didn't want to add any variation. This is why we machined the surface off the plate. Do you know what I mean? That we are purely testing these, giving the same duty cycle, the same experience to all these tools. You know what I mean? So it got very boring, got very monotonous, and Chris, who you saw in this video, and I haven't mentioned Steve Cater, who unfortunately can't be with us today. That the team did an excellent job. Do you know what I mean? It's a bit monotonous, and as I say, that it's not like exciting, but consistency was the key to this, you know what I mean? And therefore ensuring that everything was the same, tool on tool, weld on weld was very important.
Okay, thanks. Santonu and Jonathan, I guess probably Santonu first, is there's quite a lot of questions about the image of the tool and whether or not it was cleaned off before measuring. If so, how was it cleaned off? And do you think the tool can leave contamination in the weld at all?
Well, if the question is related to the wear measurements, the one interesting part we noticed is that the tools were there is no lot of steel adherence on the tool, even with the longer length. So we didn't clean these tools for any kind of special cleaning technique to remove the steel or any other part, which is mostly steel is adhering to the surface. However, we cleaned it to the level where the optical imaging is possible. So we kept the tool intact.
Okay, thank you. Quite a lot of questions about the actual makeup of the tool. I think one or two people want to know exactly how you make it, Santonu, so maybe you could describe that, but no, don't. I think quite a lot of understanding of exactly what the PCBN material is. Could you describe again a little bit about the material that's actually used?
So PCBN, I don't know so the background, but I'll just tell you the polycrystalline cubic boron nitride is a composite ceramics. So you have CVN, and then you have the binder phase, we call it. And there are two different kind of broad categories of PCBN. One is we call low content PCBN, where the CVN content is around 40 to 70% CVN content, and then there is high content CVN, where the CVN content increases from 70 to 90% CVN. The binders, as Abhishek mentioned, we have a lot in the product range, and we play around with the binders quite a bit. So, but make sure in this case specifically, our target was to make a PCBN which has very good high temperature properties. So we chose the material such a way, and also the toughness wise, it's better so that it can withstand the harsh impact of a plunge.
Okay, thank you. Quick question on the 40-meter welds that people have seen. How many plunges did we do across those 40 meters? And did we pre-drill the plunge?
So there were 8 5-meter. So there was 8 plunges and 8 5-meter welds. Okay. Yes, there is a small pilot hole that we use in order to plunge the tool into. This was mainly to stop really the material coming out of the workpiece causing problems with the tool. We think that perhaps we can eliminate the need for the pilot hole, but in order that we didn't want to change the tool design at the time, so we drilled a very small diameter pilot hole that the tool then plunged into. So each of these 40-meter welds, there were 8 plunges and 8 5-meter long welds.
And just to raise another point, so in this trial, the results you're seeing, we made pilot holes, as Jonathan was mentioning. We did test this tool without pilot hole even, but since in this case we just wanted to keep everything constant, so all these runs we had the pilot holes.
Okay, thank you. A lot of questions about the thickness and how thick we can go, which we've answered. But I think that indicates that I think people will be very interested, Santonu and Jonathan, about developing a thicker capability, which is interesting.
If I make one request in that case is that if you have any application, right, we mentioned about the pipeline, or if you have any application where you want to test this tool to thicker plates, please get in touch with us or TWI, and we can work in collaboration on that.
Okay, thanks. Question from Nikki: what is the NDT capabilities for friction stir welding of steel, and is it relatively accurate? I guess that's probably Jonathan.
Yeah, obviously NDT is used. We haven't done that much on steel, but I would imagine, you know, the NDT techniques for inspecting aluminium are reasonably well developed now in terms of phased array, etc. So the form of the weld that we're producing by steel, you know, will be subject to the same sort of flaws that you would see in aluminium. So this is perhaps voids, lack of penetration. So the type of defects that we potentially would need to assess and test for will be very similar, and therefore the techniques that have been developed for friction stir welding of aluminium, we would anticipate would read across.
Okay, and so I guess that leads me on to the question then that's been asked is what are the next stages for this development? So what do you guys, what are we going to do next after we've proved the consistency of these tools between E6 and TWI? What's the next stages? What do we intend to develop next?
I'll probably go first in terms of the tool. So yes, as Jonathan just mentioned, that there are a lot of other exciting things we want to try with the tool. Design is one aspect. We want to increase the sizes, and also going to the atmosphere point is we want to test these tools underwater. We want to test it in different conditions, different atmosphere in which this tool will be applied. So yeah, there are a lot in the pipeline in terms of development Jonathan, you'd like to add anything?
Yeah, I think we'll be very interested to hear from, you know, obviously the people on this webinar where they think these tools could be introduced and developed. I think we have our own ideas in terms of potential applications for the tools, but we would love to hear from people, you know, who have an interest, have applications, and this may then steer where this development goes. Also, obviously, we know. This is market driven. If there's interest in a particular area, particular thickness, particular alloy grade, etc., I'm sure this may colour in terms of where the research needs to go. So getting industrial feedback on the work that we've done is very, very important.
Okay, so you're going to see, well, hopefully the next developments will be more product specific as we go. Okay, that's great. We have over 100 questions, but we'll finish at 4. Sorry, but I'll just ask a couple more. One of them was the machine that you used looks very big. Does it need to be that big to do welding? What machine tools are needed to do friction stir welding?
Yes, the machine that we used here is a very large machine. So the capabilities of the current, so this work was done in the Technology Centre up in Sheffield. So we have a limited range of well, we have quite a broad range of capacity of equipment. So this machine is our power stir machine, which is used for welding very thick material. So we can weld up to sort of 75 millimeters in aluminium in one go. We have a 3D robot, or a robot for making 3D components, and we also have a smaller research machine. So in order to sort of assess these tools, we wanted to do these 5-meter long welds, and this is why therefore we put them on the power stir. But no way do you need a machine like the power stir to make these welds. As I was saying, the forces that we see here, you know, the 40 kilonewtons downforce, the rotation, and the welding force was about 10 kilonewton. So these aren't big forces. So, you know, when people come to our facility and look at the power stir, think, woo, do you know what I mean? But this machine really has been designed to try to be everything to everybody in terms of what we can put on that machine. So, you know, any sort of, not say any, but most friction stir welders operate within this sort of range. As I say, potentially you could look to putting this onto more milling machine type applications. I think the issue perhaps where steel differs from aluminium is perhaps heat management a little more. in terms of ensuring that the tool is cooled, or that you have some cooling, both to protect the tool, but also to protect the spindle bearings, and also perhaps considerations for gas shielding in terms of providing an inert atmosphere for the welding. But I say the forces here aren't anything, you know, they're not like a magnitude of scale bigger than anything else that you see with aluminium.
Okay. Question from me is how do people get involved? So if they want to know more, if they want to do some work with us, do they call E6 and buy a tool? How do we move forward? Santonu and Jonathan, I guess Jonathan.
Yes, well, we're very interested to hear from you in terms of, you know, what your thoughts are on this. So there are these emails here, that the email addresses that Nick put up in terms of contacting us. So yeah, we as I say, this is you know, we've demonstrated consistency. I think what we would like to do is work with the individual companies now in terms of trying to roll this technology, roll these tools out. I think as we engage, we would like to ensure that the tools and how you use these tools are fully covered. So in terms of ensuring that when these tools are supplied to you, that welding parameters are also given in order that you can operate these tools effectively.
Okay. Just a couple more questions, because it's nearly o'clock, and people will want to move on. Are there any standards already related to friction stir welding that are applicable to steel, or will new standards need to be developed, and certifications?
There are no sort of standards per se for steel at the moment. So there are standards obviously for friction stir welding which relate to aluminium. So there's the ISO 25239 and the American D17.3. So we have been working with sort of like Lloyd's, looking at guidelines, which hopefully will then be adopted for rules, and then leading on from that to perhaps more standards. That there is talk. I know, you know, I'm involved with some of the Standard Commission on Friction Stir Welding, and that there has been talk about doing one for steel. But I think the issue is, or has been in the past, is, you know, it's not extensively used in industry at the moment, and therefore why do a standard? Hopefully now this breakthrough will now see friction stir welding still being applied, you know, in industry, being used by industry, and therefore there will be a driver then to create the standards in order to you know, to run these welds against.
Okay, one more question before we wrap up, probably for Santonu, well, for both of you. A lot of people have asked, and Neil specifically asked about using these tools on other materials other than steel. We've talked about stainless, but what about, for instance, being able to get better tool life in aluminium, welding copper, etc.? Do we think these tools will have a life beyond just steel?
Copper, I think, will be interesting. I perhaps I'll have to defer to Santonu in terms of the affinity of PCBN and copper, in terms of the chemical affinity or the inertness of PCBN and copper. I've never seen PCBN used for copper before. Obviously, you know, most people I've seen when welding copper has been sort of tungsten and cement, Inconels, even some steel. The temperature for welding copper is less than steel. The forces, I would say, are similar. So in terms of a potential tool material for copper, other than the chemical affinity, which probably, Santonu, I'm not sure whether you know or not, I think that you know, that is perhaps a good candidate. For aluminium, perhaps. I think there are lots of different materials that can be used for aluminium. I'm not so sure whether PCBN would offer. It may offer, whether there's the cost balance between the cost of these tools to tool life for aluminium. I'm not so sure.
So yeah, I think, Jonathan, you pretty much summarized it. There are a couple of points I would like to add. One is, if you look up in the literature, you will see PCBN has been tried in different suppose in metal. However, what we want to do is to make sure that these tools is kind of successful in application. So all different applications of whether it's a copper or other metals, you would require to kind of investigate further. At this moment, the tools which we are using, and we believe that for steel, they are going to be good. We haven't looked up or tested anything on this tool. However, the answer from us will be, please get in touch and have a discussion. We can have a longer time probably than the minute I am left with.
Okay, that's thank you, Santonu. So we would encourage everyone to ask some more questions.
Yes.
Mike, would you like to say anything? We've been asked a lot. You know, do we see this as a big market going forward? Do we think that it will be as big as the aluminium market and into the future?
Yeah, thanks, Nick, and thanks everyone. I think that this webinar today and the number of participants and a great number of really good questions just underlines the interest in this area and the potential for growth. I think it's a really exciting step up in this technology, and we look forward to seeing it applied across the board.
Okay, that's great. Abhishek, did you want to say anything before we just wrap up?
I just wanted to say thank you to all of you for joining today. There's work to be done here. I think we've taken the first step, but we look forward to hearing from you, trying to develop new applications, working together, and trying to create friction stir welding in steel. So thank you again for your time. Looking forward to hearing from you.
And I think, yeah, thank you very much, everybody, Jonathan, Santonu, and everybody. And thank you for Stacey for setting it up. Just one question: is it going to be? Are we going to make the recording available? Certainly, we'll be sending out the slides. Do you know if the recording is available, Jonathan? I'm not sure. Maybe Stacey can tell me if the recording will be made available afterwards. I just want to say, whatever plans you've got for the weekend, even during lockdown, Santonu and Jonathan, you need to cancel them because you've got over 100 questions to answer. It's going to be it's going to be a busy 24 hours. So,
busy 24 hours.
and I'm not qualified, so that was terrific. Thank you, guys, and I wish you all well. And stay safe, everybody. There's more questions than we can answer today, but we will get back to everybody that has asked questions and come back to you, and we look forward to working with you in the future. Thank you very much.
Thank you.
Thanks.
Thanks. Bye.
Thanks.